So we have seen a demo of the issues related to multicollinearity. What is multicollinearity? Interdependency between the predictor variables. They themselves, all the x variables, they themselves might be dependent on each other, then that might cause into absurd results. So parameter estimates will have inflated variance in presence of What is inflated variance? So of parameters. What is inflated variance of regression coefficient? That is nothing but the way the coefficients can be anything. They can be 20 now, later on minus 20 or minus 30. With small changes in the data, the multicollinearity will cause lot of changes in the coefficients. Sometimes signs of the parameter estimates also tend to change. That's what we have observed. We have seen an inverse relation and counterintuitive inference. So in fact, the interdependency between the independent parameters will, if it really grows really strong, then the variance of parameters even get to infinity sometimes. What are the coefficients? Like sometimes even the variance of the parameter, let's say the beta value can be between minus infinity to plus infinity. It can go to that level. That is the issue with multicollinearity. So since we observed that multicollinearity is an issue, how do we detect multicollinearity? Now there is an easy way of doing it. What we need to do is, let's take an example. There are 4 variables, x1, x2, x3, x4. These are the 4 variables, and we are trying to use these 4 variables to predict y. Now if there is multicollinearity in this data, how do we find out? You might say simple correlation. Why don't we find correlations and find out? There is a problem in just finding the pairwise correlation. What is the problem? It might so happen that x1 and x2 correlation might be less, x1 and x3 correlation might be less, x1 and x4 correlation might be less, but these 3 variables together, x2, x3, x4 together, might be impacting x1. x1 might be depending on x2, x3, x4 together. Or if we fit a regression line between x1 and remaining 3 predictor variables itself, we might have got an R square of 80 or 90 or 95%. Now that is also multicollinearity. One variable can be completely explained by rest of the variables. That is not coming out from correlation. So we need to find a better way of identifying the multicollinearity or detecting the multicollinearity. So this is how we do it. We have this model y versus x1, x2, x3, x4. Since we are detecting multicollinearity, since we are talking about only multicollinearity that is related to only predictor variables, we will keep aside the dependent variable, or we'll keep aside that y variable for some time. We will not consider that because multicollinearity has something to do with only predictor variables. Now build a model x1 versus x2, x3, x4. Why am I doing that? What I'll do is I'll find the R square of such model. This is a different regression model within predictor. If that R square is higher, if that particular R square, x1 versus x2, x3, x4, that R square is 98%. What does that mean? I'm fitting a regression line between x1 and remaining 3 variables, x2, x3, x4. And that R square, I got it as 98%. Can I say there is multicollinearity? Can I say x2, x3, x4 together explain 98% of the variation in x1? Can I say that x1 is redundant in presence of x2, x3, x4? Can I say x1 simply can be dropped, otherwise it will lead to multicollinearity? Yes, we can say that. If we build a model x1 versus x2, x3, x4 and we have an R square which is not really high, just 20 or 30%, then we can say, yeah, x1 is carrying some independent information. It is not same as x2, x3, x4 together. Similarly, we can build a model x2 versus, so that is just for finding multicollinearity or relation of x1 with remaining 3 variables. Similarly, we repeat the same thing, x2 versus x1, x3, x4. Say R2. x3 versus x1, x2 remaining variables, x4 versus remaining variables. If any of these is more than 95%, then we don't really need that variable. because we are finding individual variables using rest of the variables. So if rest of the variables are explaining almost all the variation in this particular variable, then there is no point in keeping that particular independent variable. Even if we keep it, then it will lead to multicollinearity, then that will lead to lot of variance in the regression coefficients, or the regression coefficients might go wrong. So how do we detect multicollinearity? Instead of finding these R squares, which will be again confusing, we will find something called VIF, which is nothing but 1 by 1 minus R square of these individual models I'm talking about. I'll find VIF of x1, that is this R square, 1 by 1 minus R square, VIF of x1, VIF variance inflation factor, VIF of x2, VIF of x3, VIF of x4, like that. So we just need to find VIF values. So there is a function in R which will automatically calculate VIF values. Simply you give the model and you calculate the VIF values. Then depending on the VIF, if R square is more than 80% for a particular variable, so if this R square is more than 80%, then we will say x1 can be explained by these three, then we'll say there is multicollinearity. Similarly, at an 80% R square, if you substitute 1 by 1 minus 80%, you will get VIF of 5. So for any variable VIF of more than 5, that means that variable can be explained by remaining all the variables. Then that variable can be dropped. So we will see that in a lab in just now, but before that we need to understand that multicollinearity might come in pairs. What do I mean by that? Let's say in presence of x1, x2 is redundant. In presence of x2, x1 is also redundant. So while I am calculating VIF of x1, I am using x2, x3, x4, VIF of x1 will be higher. VIF of x2 and I am using x1, x3, x4, that also will be higher if these two are related. That doesn't mean I should drop both x1 and x2. If I am dropping both of them, then I am losing out the whole information altogether. I have to drop any one of them so that multicollinearity will be lost. Like in presence of other variables, this is redundant. So let us see what exactly I mean to say multicollinearity or VIF value comes in pairs. But for now you have to understand that VIF is the measure for detecting multicollinearity. So let us see on the final exam data, how do we find the VIF values. So to calculate the VIF values, we need a package called car in R, companion to applied regression. You have to install that package. And then I'm building the exam model. Okay. Here we have observed multicollinearity, or we want to detect multicollinearity. This is the summary with all the 4 variables. Now I'll write something called VIF of final exam model. That will give the VIF values. VIF of more than 5 means dangerous. VIF SEM1 is also high, SEM2 also high, SEM1, SEM2 math. So we have already observed SEM1 mathematics, SEM2 mathematics are anyway related in this graph, or even we found the correlation. We found their correlation also to be really high. SEM1 mathematics and SEM2 mathematics 95% correlation. But anyway, we will not use correlation for detecting multicollinearity. We will use VIF value, VIF of exam model. Now we should not drop both semester 1 and semester 2 mathematics, because in presence of semester 2, semester 1 is redundant. In presence of semester 1, semester 2 is redundant. We have to drop the highest one. So we will drop the semester 1 mathematics. Once I drop it, then the second one will be auto-corrected. So what I am doing here, I am building model 1, whereas I am using only science, math, only one math. I'm dropping it. I'm expecting this to get auto-corrected. I'm expecting there should be no multicollinearity, at least in terms of semester 2 mathematics. Again, I'll find the VIF. R square is good, adjusted R square is good. What is the VIF value? Semester 2 mathematics, VIF changed, right? Less than 5. We should not drop both semester 1 and semester 2. Is there still multicollinearity in this data? Yes. Looks like semester 1 science has higher than 5, semester 2 science has higher than. I'll go one step further. I'll drop even semester 1 science. Why am I dropping that? Because VAF is more than 5. That means this variable can be explained, almost 80% of this variable can be explained by remaining 2 variables. That's why I am dropping that. Good R square, because we are not losing out on any information. And then what is the final VIF values? VIF is less than 5. Do I need to drop any of these variables? No, because both of them are less than 5. So that is how we detect multicollinearity. If there is multicollinearity, we can drop the variables, because that is kind of redundancy. In presence of that variable, we don't need remaining variables. That's the reason why we drop the variables that are showing signs of multicollinearity. Similarly, there is one exercise I would like you to do that. That is in the air passengers data, find out the multicollinearity. So we need to drop variables one by one. We can't drop all the variables that are more than 5%. 5 as the value. We can't drop all the VIF values more than 5 and say we reduce multicollinearity. If that is the case, in our model we should have dropped all the 4 variables, right? We have to reduce multicollinearity. We have to drop the variables one by one. Okay. Now, multiple regression model building. So we are kind of done with all the important topics that we should discuss in regression, simple regression, multiple regression. What are the metrics that you should do? What you should see? What are the most impacting factors? How do you identify them? What is multicollinearity? What is the p-value? All those things. So you have to use all of them and build a multiple regression model for web product sales data. Web product sales depends on so many other variables. So product sales, then based on that you have to see most impacting variables. You have to reduce multicollinearity, do all these tests. You have to look at R square, you have to look at adjusted R square, you have to find out whether there are any junk variables. So this will give you a complete deep dive into whatever concepts we have learned till now. Please do practice whatever whatever which says lab. Then after doing all those labs, again you come here, you will be doing the entire one specific business problem, that is web product sales. Understand the problem, understand the variable, then solve it. Conclusion.